Welcome to another episode of Science to Sleep By. Tonight, we're slowing everything down far down until we reach the smallest scale nature allows, a place where the smoothness of space dissolves, where time itself begins to jitter, and where reality becomes a frothing sea of quantum uncertainty. This is a peaceful exploration designed for us audience who love science, mystery, and the comfort of drifting off while learning something profound. So settle into bed, let your breathing soften, and prepare to travel to the most hidden layer of existence, the unimaginable frontier known as the Planck length, to understand what the Planck scale truly represents. Imagine shrinking yourself down past every familiar frontier of size, drifting smaller than atoms, smaller than the orbiting electrons, smaller than the nucleus, and smaller still, even the quarks that make up protons lose their distinct identity. And beyond that, until the very idea of a particle becomes vague and uncertain. The Planck length sits far below all of these, at a realm where distance as we understand it stops being a smooth, continuous fabric, and instead becomes something grainy, jittery, and fundamentally limited. It is a number so small that writing it out feels almost absurd. Roughly 1.6 times 10 to the minus 35 meters. A scale so tiny that if an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a single tree on a single planet somewhere inside that cosmic structure. This scale is not chosen arbitrarily, but emerges naturally when you combine three constants that define the deepest rules of nature: the gravitational constant, which determines the strength of gravity; the speed of light, which determines how fast information can travel; and Planck's constant, which defines the granularity of the quantum world. When these three pillars of physics are woven together mathematically, they produce the smallest possible unit of length, a scale where the gravitational field of even the tiniest vibration becomes so strong and so dense that it folds into quantum behavior in ways we do not fully understand. As you ease yourself deeper into this concept, laying comfortably and letting the idea sink in as softly as your head sinks into your pillow, the Planck length begins to reveal its most profound meaning. It is the threshold at which gravity and quantum mechanics, two theories that normally live in separate domains, one for planets and stars, the other for particles and probability clouds, collide with such intensity that they cannot be treated independently. In the everyday world, gravity seems tame, predictable, and classical, while quantum mechanics is strange, probabilistic, and elusive. But at the Planck scale the distinction vanishes and both systems refuse to stay in their assigned categories. The mathematics suggests that spacetime itself becomes so energetically unstable at this size that you cannot speak of position, shape, or location in any smooth way. Every attempt to measure a smaller distance would require so much energy, compressed into such a tiny region, that the region collapses into a miniature black hole, which hides any information you were trying to gather. This limitation hints that the Planck length is not just tiny, but fundamental, marking the smallest unit of space that can exist in any meaningful physical sense. Lying there in the quiet, you might feel the mind naturally drifting as the Planck scale begins, shifting from a number into a concept, into a boundary of nature that does not break, but instead whispers that reality is not infinitely divisible. You might picture the universe as a painting, and the Planck length as the smallest brushstroke the artist could ever use, no matter how fine the brush becomes. Zoom in beyond that stroke, and the painting dissolves into abstract texture, a pattern that has no smaller parts, no matter how intensely you stare at it. This is the role of the Planck length in physics. It defines a pixel size for the universe, a resolution limit. Just as a digital screen cannot display details smaller than 1 pixel, the universe cannot contain meaningful spatial features below 1 Planck length. Above that, space behaves smoothly enough that geometry, distance, and shape make sense. Below that, the universe refuses to show us finer detail because there is no finer detail to reveal in this peaceful moment. Consider how extraordinary it is that such a minuscule length controls the behavior of everything in existence. The Planck scale provides the stage on which the drama of quantum gravity plays out, shaping black holes, influencing the earliest instant of the Big Bang, and governing the most extreme environments where energy density becomes unimaginable. Even though we cannot observe anything at this scale directly, the Planck length leaves fingerprints on the large-scale universe in the form of quantum fluctuations in the early cosmos, fluctuations that later grew into galaxies and clusters through gravitational attraction. That means that while the Planck scale is unfathomably small, its effects echo across billions of light years, stretching from the early universe to your own quiet room at this very moment. Scientists continue to study this scale, not because they expect to shrink down to it physically, but because understanding what happens there could unify the forces of nature into a single elegant description. Every time you imagine shrinking closer and closer to this boundary, you are approaching a point where physics transforms into something we have not yet fully solved, something that feels almost mystical in its uncertainty, yet grounded in precise mathematics. This edge of understanding invites the human mind to wander, to soften, and to rest in the mystery rather than chase a definite answer. Thinking about the Planck scale becomes a meditative practice, a reminder that even the universe has limits built into its structure, limits that protect the coherence of reality. At the Planck length, the rules flicker, space trembles, and time loses its continuity, not as a failure of physics, but as a gentle reminder that below a certain threshold, questions themselves lose meaning. The Planck scale, therefore, becomes not just a frontier of science, but a quiet philosophical boundary. It is the universe telling us, softly, that there is a smallest step, a smallest moment, a smallest vibration, and beyond that lies only uncertainty, pure potential, and the whisper of spacetime's deepest secret. As you drift gently into a calmer state, imagine the universe not as a still, silent expanse, but as something quietly restless beneath the surface, like the ocean viewed from far above. From a distance, the ocean looks smooth and undisturbed, but if you descend closer and closer, the stillness dissolves into ripples, waves, and intricate whirlpools of motion. The fabric of spacetime behaves in a remarkably similar way. At everyday scales, space appears stable, serene, and continuous. At the atomic scale, it begins to feel more dynamic, animated by vibrating fields and shifting probabilities. But if you descend even deeper, shrinking all the way down to the unimaginable realm of the Planck length, the calmness evaporates entirely. What emerges instead is something physicist John Wheeler poetically called quantum foam, a seething, flickering, unpredictable landscape where the smoothness of spacetime tears apart into tiny, constantly shifting curvatures. Let the idea take its time as it settles into your thoughts, much like watching tiny ripples spread across a quiet pond. At normal scales, we treat spacetime as a kind of invisible stage upon which all matter and energy play their roles, a steady background that bends slightly around planets and stars, but remains mostly flat and dependable. Yet the equations of quantum physics insist that no field, not even the gravitational field that shapes spacetime itself, can remain perfectly still. Everything in the quantum world fluctuates, vibrates, jitters with restless energy. And as you shrink the region of space you're examining, these fluctuations become more and more dramatic. By the time you reach the Planck length, the fluctuations are so intense that spacetime is no longer a calm, smooth arena, but a roiling bath of microscopic distortions. Distances stretch and compress unpredictably. Tiny wormholes flicker in and out of existence. Curved regions collapse into miniature black holes one moment and evaporate the next. The vacuum itself becomes noisy, turbulent, and alive with possibilities. You sink into the softness of your pillow. Imagine these Planck scale fluctuations not as violent disturbances, but as a delicate dance, an infinite shimmering beneath the surface of existence. At this level, quantum uncertainty takes over fully, making it impossible to speak of a definite shape to space. Instead, you have a frothing mosaic of temporary geometries. One moment space curves inward sharply, the next moment it bulges outward. You can picture spacetime like the foam on top of a cup of coffee, where bubbles constantly form, merge, and disappear in an ever-changing pattern. But unlike foam on a drink, Quantum foam has no underlying liquid or container. It is the structure itself, the raw, primitive form of spacetime before it becomes smooth enough to support stable objects like atoms, planets, or galaxies. This image, though abstract, offers a comforting sense of the universe's depth. Even while you lie here in the stillness of your room, the bed beneath you unmoving, the air quiet and calm, the universe at its smallest scales is anything but still. It churns with fluctuations that are impossibly rapid, far faster than any vibration you could sense. These fluctuations arise from the inherent uncertainty that governs energy and time. The shorter the timescale, the larger the energy fluctuations allowed by nature. At the Planck timescale, roughly 10 to the minus 40 seconds, energy fluctuations become tremendous, so large that they distort the geometry of spacetime itself. This isn't a disturbance added to spacetime. It is spacetime. There is no deeper layer of calm beneath it. Quantum foam is the fundamental texture from which all smoother structures emerge. Physicists believe that this foamy, turbulent activity is not simply theoretical noise. Instead, it shapes the universe in profound ways, providing the microscopic seeds that determine how spacetime behaves on cosmic scales. The smooth, expanding universe we observe today is like the surface of an ocean that appears flat when viewed from an airplane. But knowing that beneath that surface lies a churning, wave-filled body of water helps explain why the ocean behaves as it does, why waves emerge, why currents flow, why storms build. In the same way, quantum foam may hold the key to understanding phenomena like the vacuum energy that accelerates cosmic expansion, or the fundamental difference between matter and antimatter, or even the origin of tiny quantum fluctuations in the early universe that later grew into galaxies. All of these large-scale features may trace back to the restless activity of spacetime at its tiniest scales. As you breathe slowly and evenly, imagine spacetime not as something distant or abstract, but as the foundation beneath everything you see, touch, and experience. Every atom in your body, every beam of light that enters your eyes, every vibration of sound around you, all rely on the stability of spacetime. Yet, this stability emerges from a wildly unstable underlayer, a chaotic quantum foam that somehow averages out into the calm environment you experience. This contrast between the violently fluctuating Planck scale world and the peaceful macroscopic universe creates a strange sense of comfort. It suggests that even when things appear quiet, there is a profound depth beneath them, a hidden complexity that supports the tranquility. You enjoy lying here, you can let your mind drift over this picture. Like watching gentle waves from the shore, you do not need to analyze the details or solve any equations. You can simply feel the weight of the idea, the soothing paradox, that beneath the universe's stillness lies an ocean of motion. The quantum foam behaves like a kind of cosmic heartbeat, pulsing at unimaginable speed, sustaining the fabric of reality. In its flickering patterns, the seeds of everything that exists are continuously shaped and reshaped. It is the ultimate reminder that even in the smallest, most hidden places, the universe never truly rests. It vibrates, fluctuates, and foams with endless possibility, creating a foundation that remains forever alive, forever dynamic, and yet balanced enough to allow the larger cosmos to appear serene, steady, and gently unfolding around you as you settle deeper into comfort and let your breathing fall into a slow and steady rhythm. Imagine the familiar idea of geometry gently dissolving in your mind. Geometry is something you've known your entire life, without even thinking about it. Straight lines, smooth curves, angles, distances, shapes that remain the same no matter how closely you look at them. You trust these things instinctively. A line is a line, whether drawn on paper, carved into stone, or traced across the sky. A circle stays a circle whether you zoom in or zoom out. In everyday life, and even at the level of atoms, geometry behaves with reassuring consistency. The universe seems to follow rules we can describe with clear equations and clean sketches. Space feels continuous. Distances make sense. Angles behave predictably. But as you begin to drift into a deeper imaginative space, shrinking down in thought far beyond molecules, far beyond the vibrating edges of particles. And deeper still, in the realm hidden beneath all physical structure, something remarkable happens. Those familiar concepts begin to fall apart. This breakdown doesn't happen suddenly but subtly, like fog rolling in across a landscape you once recognized. At first, you may picture space as a smooth grid, a clean and infinite stage. You imagine it divided into smaller and smaller squares, each one representing a tiny portion of the universe. But as you shrink those squares closer to the Planck length, so impossibly small that no physical instrument could ever resolve them, the clarity of the grid begins to fade. The perfect lines wobble, the corners blur, the straightness you took for granted becomes unreliable. This is the first hint that classical geometry, the geometry you learned in school, and that shapes nearly everything you see around you, is not fundamental. It is an approximation, a useful but incomplete description that breaks down under the intense quantum fluctuations that dominate the Planck scale. The smoothness of space is like the smoothness of a wooden table that seems perfectly polished until you examine it under a microscope, revealing ridges, pores, and jagged imperfections that were invisible from above. Allow your mind to explore the idea more deeply, without rushing, as though you are floating slowly downward through layers of reality. In the world described by general relativity, spacetime is a continuous fabric that curves gently or sharply, depending on the mass and energy it contains. That curvature is well described by Einstein's field equations, which envision spacetime as something that can bend, but not fracture or dissolve. Yet as you push the equations to smaller and smaller scales, they begin predicting infinite curvatures and impossible quantities. This is a sign that the classical view of spacetime is reaching its limits. Physics reacts to these infinities the same way the body reacts to pain. It signals that something is wrong with the current description. Spacetime cannot remain smooth at the Planck scale because the equations describing that smoothness stop making sense. They become unstable, chaotic, and undefined. Just like a map that becomes nonsense once you zoom into far, revealing blank areas and overlapping lines where no detail exists as you lie quietly. You might imagine trying to draw a perfectly straight line on a surface that is constantly trembling. Each time you press the pencil down, the surface shifts, the line tilts unpredictably, and what should be straight becomes jagged. At the Planck scale, spacetime behaves like that trembling surface. Quantum fluctuations cause the geometry to dance uncontrollably, with distances expanding and contracting in bursts too rapid to measure or even conceptualize. If you tried to draw a circle, it would warp into something unrecognizable within a fraction of a second. If you tried to define a distance, the value would shift unpredictably before you could finish the measurement. This instability is not a defect in spacetime, but a natural consequence of combining quantum mechanics with gravity. The closer you get to the Planck scale, the more intense these fluctuations become, until the very idea of a continuous line loses meaning. Now imagine trying to define something even simpler, a point. In classical geometry, a point has no size, no shape, no width. It simply exists as a location. You can mark a point anywhere, and no matter how closely you zoom in, it stays a point. But at the Planck length, this notion collapses entirely. A point cannot exist without defining a position with infinite precision, and to measure a position with infinite precision, you would need infinite energy. Infinite energy packed into a tiny region would create a gravitational field so strong that it would collapse into a miniature black hole. The attempt to define a point destroys the point itself. This paradox reveals something profound. The universe does not allow infinitely small locations. Space is not infinitely smooth or infinitely divisible. Instead, there is a smallest possible meaningful region, and below that, the very concept of location evaporates. The geometry you've known your whole life simply cannot survive here. Let this realization wash over you gently. Not as something alarming, but as something serene. Like learning that a familiar trail leads to a misty forest where the path softens into earth and moss. The breakdown of classical geometry is not a failure of the universe, but a natural transition into a realm where different rules apply. The universe is whispering that its foundations are more mysterious, more intricate, and more alive with motion than the clean lines of Euclid or the smooth curves of Einstein suggest. At the Planck scale, space may be discrete rather than continuous, woven into tiny, granular units instead of flowing as a seamless fabric. Or it may twist into loops, strings, or networks that defy the language of classical geometry altogether. Whatever the true form of spacetime is at this depth, it is something fundamentally different from the picture we inherit from everyday experience. As your body relaxes further and you feel the weight of the day slipping away, the idea settles into a comforting truth. Geometry, as beautiful and reliable as it is not the ultimate architecture of reality. It is a large-scale pattern that emerges out of a deeper, more vibrant microscopic world. The breakdown of classical geometry at the Planck length reminds us that the universe holds mysteries far beyond our immediate perception. Mysteries that hum quietly beneath the surface of everything, waiting patiently for us to approach them with imagination, curiosity, and a sense of calm openness as you settle into the slow, soothing rhythm of your breath. Imagine the universe not as a silent emptiness, but as an intricate orchestra of vibrations, hidden beneath every atom and every corner of space. When classical geometry dissolves at the Planck scale and spacetime becomes wild and foamy, physicists begin searching for deeper structures that might restore order to the chaos. They look for something more fundamental than points, more stable than smooth distances, something that explains why particles exist and why forces behave as they do. In this hushed and curious search, two of the most compelling ideas in modern theoretical physics emerge: string theory and loop quantum gravity. These frameworks are not complete answers, but gentle possibilities, quiet glimpses into the hidden fabric beneath the quantum foam. They offer pictures of the Planck scale world that are radically different from anything we see in the familiar universe. And as you let your mind drift deeper, these possibilities settle into your imagination like soft lights in the distance. Begin with string theory, a concept that replaces the idea of point-like particles with tiny, vibrating strands of energy. These strings are unbelievably small, curled up at the Planck length, so fine that no microscope or instrument could ever reveal them directly. Instead of particles being dots without size or structure, string theory imagines them as loops or segments of one-dimensional energy that can vibrate in countless distinct modes. Each vibration corresponds to a different type of particle. A photon is a string vibrating one way. A quark is a string vibrating another. Gravity arises from a specific vibration called the graviton. In this view, the universe is not built from solid building blocks, but from musical notes played by the tiniest possible strings. This metaphor offers a soothing, harmonious image. Reality as a cosmic symphony. Every particle a tone, every interaction a chord, all woven from rhythms too small for the human eye, but fundamental to the structure of everything. The beauty of this idea lies not only in its elegance, but in the way it naturally incorporates gravity. In ordinary quantum physics, gravity resists quantization. It refuses to behave like the other forces of nature. But in string theory, gravity emerges automatically from the vibrational patterns of strings. The theory does not force gravity into quantum form, it flows from it. This is a profound shift in perspective. Instead of seeing gravity as a curvature in smooth spacetime, string theory sees it as a consequence of the underlying music played at the Planck scale. The foaming, jittering chaos of spacetime becomes an ensemble of vibrating threads that create order through resonance. Spacetime itself may not be continuous, but may instead arise from the interactions of these strings, the way fabric emerges from interwoven threads. In this picture, the Planck scale is not a place where geometry breaks, but a place where geometry is born, where the smoothness of space emerges from countless tiny oscillations working together. It as soothing as this picture may be, string theory requires dimensions beyond the ones we experience. To remain mathematically consistent, it often invokes 10 or 11 dimensions of spacetime, with the extra dimensions curled up tightly at the Planck length. These hidden dimensions are not empty, but shape the way strings vibrate, influencing the properties of particles and the nature of forces. You can visualize these dimensions as tiny shapes folded into each point of space, like minuscule origami structures impossible to unfold. Though invisible to us, they guide the universe quietly, like the unseen workings inside a clock guiding the movement of its hands. This idea invites a sense of wonder, a gentle reminder that what we perceive with our senses is only a thin slice of reality, and that beneath the familiar surface lies a rich geometric tapestry, too small and too curled to ever reveal itself directly. Now let your thoughts drift to the contrasting idea of loop quantum gravity, which seeks to quantize spacetime itself rather than the particles within it. Instead of strings, this theory imagines that space is built from finite units, tiny loops woven into a network called a spin network. These loops are not objects floating within space. They are space. They form the fundamental weave of the universe, like threads forming a fabric. In this vision, area and volume come in discrete chunks, instead of flowing continuously. Space is granular, made from indivisible units, each shaped by the way loops connect and interact. If you picture spacetime as a smooth ocean from afar, loop quantum gravity invites you to zoom in and see that the water is made of droplets. The geometry that seems continuous at large scales is actually quantized at the Planck scale, with no structure smaller than the loops themselves. This granular view of space leads naturally to a world where classical geometry breaks down. But a new kind of geometry emerges, one built from nodes and links rather than curves and coordinates. At larger scales, these loops blur together, forming the smooth spacetime described by Einstein. But up close, spacetime loses its familiar texture and becomes a mosaic of tiny relationships. Time itself is thought to advance in discrete jumps rather than flowing smoothly, much like the ticking of a clock, so small and so rapid that its steps feel continuous at human scales. This idea replaces the turbulence of quantum foam with a more structured, though still incredibly dynamic, foundation. Quantum foam may still exist, but it arises from the fluctuating connections of these loops rather than the endless instability of classical geometry. As you sink deeper into your comfortable position, both theories begin to blend gently in your mind. Whether reality is made of vibrating strings or networks of loops, whether spacetime emerges from waves or from granular units, the message is the same. The Planck length is not an empty void, but a threshold where the universe changes its language. It stops speaking in lines and distances and begins speaking in vibrations, loops, and mathematical structures that are too fine to visualize directly. These theories, though different, share a common principle. They treat spacetime not as a passive stage, but as an active participant in the universe's dynamics. They suggest that at the smallest scale, the universe becomes playful, creative, and full of structure. Even though it appears chaotic when viewed from the lens of classical physics, allow this idea to rest gently in your thoughts. Beneath everything you know, beneath every star and every atom, beneath even the vacuum of space, lies a realm of structure so delicate and fundamental that it shapes the entire cosmos without ever revealing itself. Whether through strings humming at unimaginable frequencies or loops linking in geometric harmony, the Planck scale holds the blueprint from which all reality emerges. It is a quiet, hidden orchestra of structure, rhythm, and connection, continuing its ancient performance at every moment, shaping the universe softly, patiently, and invisibly. As you drift into deeper stillnesses, you breathe gently and allow yourself to sink deeper into calmness. Imagine peeling back the layers of the universe until you reach the smallest, most delicate realm where the familiar rules of nature dissolve. One of the most important of these rules, something that quietly shapes every atom in your body and every particle in existence, is the uncertainty principle. At everyday scales, you rarely feel its presence because the uncertainties are tiny, almost invisible. But the uncertainty principle is always there, whispering through the quantum world, reminding us that nature never allows perfect knowledge of certain pairs of physical quantities, like position and momentum. You can know one more precisely only by sacrificing your knowledge of the other. This principle is gentle and subtle when dealing with electrons, photons, or molecules. But when you approach the Planck scale, the uncertainty principle stops whispering and begins to roar. To ease into this idea, imagine holding a flashlight in a dark room. When you shine it onto an object, you illuminate it, making its position clearer. But at the quantum scale, illuminating something requires shining light with higher and higher energy.